Yes, my name is Piotr Gabryanczyk, I'm not Kevin Hammond. So this talk is going to be about Scala, Akka, and concurrency. So if you don't want to hear about that, now is the time to run away. Okay, so first thing I'm going to talk about today is going to be how to improve your performance of your system. So I'm going to improve performance of the example system 2 times, so by 100%, without losing, hopefully, without losing simplicity, keeping it as simple as it was before. And then I'm going to show you how to improve the throughput of your system by 10 times. Using asynchronous I/O combined with asynchronous and parallel programming, and then eventually I'll try and show you practical example of actors, Akka actors. So I used to work for this company called Zeebox. Zeebox is a social television platform, and it has a concept of a user, and the user has friends. So what we would do when the user signs in or signs up, we would go to Facebook or Twitter and we would fetch their friends. So then you obviously would merge them together, save it to the database, and then send notifications to your new friends that they can now communicate with you over Zeebox. So this is how the code would look like for this procedure. We call it update friends. So first thing we do is we fetch the user from the database, our internal database. Then we go to Facebook and Twitter, fetch the graphs, merge it, and save the user and send notifications. So this procedure would actually, as a result, would generate a number of notifications, so added and removed users. And what we would do at the end is we would wrap that, the result of this method with try type. We don't want unnecessary exceptions, we just want to nicely wrap it using try. So this method, you can imagine it runs inside of some sort of HTTP container. So HTTP thread would go and call this function, and it would block and wait until it finishes. So I'm using red arrow here on purpose because blocking is really bad. So let's see why. So if we look at the durations, average durations of various operations, the save and fetch user from internal database are relatively fast. It's 6 nanoseconds and 12 nanoseconds. The bad guys here are the Facebook and Twitter APIs. On average, they take 2 seconds. Sometimes we have outliers of like 30 seconds or timing out. But average is 2 seconds. And then notifications, sending notifications to friends around 1 second each for removed and added friends. So in total we've got 6 seconds. And on the machines we were hosting our service, we were able to spawn maximum 1,000 threads. So if you take 1,000 threads and each request takes 6 seconds, that gives you a throughput of 166 requests per second. This sounds good. If you're running a small website for your local community. But one day, the CEO of our company came to me and said, look, we're going to have an advert during the Super Bowl in US. So you can imagine, he was scared. We need to do something about this. Okay, before we go any further, I've seen this nice table at the Coursera course. It was actually used by Eric Mayer in his Coursera reactive course. It was originally put together by Peter Norwood. This is just a table showing how long various operations take on modern machines. So one CPU instruction would be 1 nanosecond. Reading 1 megabyte from RAM would be 250,000 nanoseconds, and sending packet from US to Europe and back would be 150 million nanoseconds. So these units are fairly abstract. So that's why Eric Mayer came with a trick where he actually replaced nanosecond with second, and then converted these durations into more meaningful human durations. So now CPU instruction would be 1 second, and then reading 1 megabyte of RAM would be 3 days, and sending packet to US and back would be 5 years. So that really shows the orders of magnitude. That really shows how blocking stuff is, how huge is the blocking stuff. 5 seconds versus 1 second, for running one CPU instruction. So let's annotate our function with this human terms, right? So now you can clearly see that the core of our function, which is merging, seemingly the most complex part of our procedure, takes 6 hours, and then API calls to Twitter and Facebook 55 years. I don't have to comment on that, right? So, so in total we've got 170 years in 6 months and 6 hours. So we clearly can benefit from some sort of parallelization here, because lots of these things can happen independently. So let's start doing parallelization using futures. So futures originally come from, I know there are different varieties of futures available for Scala, but the ones I'm going to be talking about come from Akka. Now they are available since Scala 2.10. They are available just as part of standard library. So, so what are futures? Futures are the way of running computations in parallel. So let's say we wanted to produce an apple. In order to produce an apple, we want to plant a tree, water it for 5 years, and then we pick the apple. So that's quite long. We want to run it in parallel. We can wrap it with the future category braces, and that will run in parallel. That will return a future object. And now, when the future completes, it would be nice to get some sort of notification. So we can use onComplete method to register callbacks. And callbacks were just functions from apple to nothing. So when that future finishes, it will call these methods, these functions, and they clearly have to be side-effecting functions because they don't produce anything. So sometimes it's useful also to convert our future. So say we had a function from apple to orange. What we could do is we could use map combinator on the future, and that would produce a future of oranges. So let's say we have really hard calculation, which produces a double. Because it's hard, we're going to wrap it in a future. So it's going to produce a future of a double. And then we want to, before we return it, we want to convert it to string and wrap it with the string. So that's why we're going to use a map function. And what map function does, it converts the future of double to future of string using that res, equals greater than, result is whatever. So that will give us a future of string. Now we can register callback and print it out. So what this code is going to do, it's going to print out I'm done here, obviously, because that will happen much earlier than the future finishes. And then it will print out success of that string. So actually, what I didn't say yet is that the onComplete actually, when it calls the callback, it actually doesn't pass the apple, but it wraps it with the try type. So in case some computation throws an exception, it will return a failure object with the exception. If it succeeded, it will just give us a success object with the value. So, okay, so let's start parallelizing our update friends. So first thing I did is I took fetch user and I wrapped it with the future. So now it's non-blocking and it returns a future. Then what I did is I used map to pass that value of a future when it finishes to the rest of the program. So you can consider the rest of the program as a continuation to that future. So once that once that user will come back from the database, this program will run, and that will produce a future of type int, because that inner block returns number of added and removed friends. Now, one more change I've done to to this method is I've added parameter. I'm passing a response object. So HTTP thread passes the response object to this method, and this is useful because what we can do is we can register a callback, which when the whole operation finishes, is going to write directly to the response. So that way, our function update friends is no longer blocking. What we do in this function, we just spawn a parallel computation, and we register on complete callback, which is going to write the response when it's ready. So that way, HTTP thread is free to handle other requests. So that's a huge thing. Obviously, we haven't parallelized much. We just made things asynchronous, but we managed to free the HTTP thread so it can do further processing of things. So the next logical thing to do would be to parallelize the API calls to Twitter and Facebook. But if we try and do this, we'll have a problem because that call, if we convert it to something which returns future, will give us a future of a future. So we need to find a way of combining those futures. Luckily, Scala futures are monadic, so they have this flat map combinator, which helps us to do exactly that. So if we have a future of Apple, and then we have a function which, based on the apple, produces future of orange, that can convert it to future of orange. Or if you want a more meaningful example, let's say we work for a bank, and what we want to do is we want to produce an account balance for the user. So first thing we need to do is fetch the user record from the database, and then once we've got the user record, we can fetch their account balance. But both reading the record of the user and reading the balance are futures. So now we can combine the two, and as a result, we can get a future of double. So if we say we pass that future to some further programs, they don't have to know how we obtained that account balance. They just care about the fact that they've got a future of double of bank account. So that's great. So let's come back to our really hard calculation example. Now I decided that I want to render HTML. After I obtain my double. So I've got this rendered as HTML, and this is slow, so I'm going to wrap it with the future as well. So we got this X future, which is a future of double. Now what we can do is we can just flat map that with render as HTML, and that will give us future of string. And then once we've got the future of string, we can do the usual, register callbacks, do map on it, whatever we want. So let's apply that to our update friends. So I made the fetch Facebook friends asynchronous as well, wrapping it with the future. And now I'm applying exactly the same trick as before to the fetch Facebook friends, because fetch Facebook friends will produce a future of Facebook friends. Then we map the rest of the program to get the future of int. And then we've got these two futures now, right? We've got this inner and outer future. So in order to compose them, we're just going to call flat map. So before we were calling fetch user map, now we're calling flat map. So I could go further, and I could parallelize all these synchronous calls, so like fetch Twitter friends, maybe merge, maybe save later on in notifications. But that would produce a very, very nested structure. So this is not what we want to do. Luckily, Scala has for comprehension, which understands monadic structures and which lets us rewrite flat map, a series of flat maps followed by map using for comprehension. So how the for comprehension works? So it takes the value contained by some sort of container. In our case, it's a future, and extracts it and sets the variable on the left. So what's going to happen is future of 1. So what it's going to do is it's going to extract 1 and set the variable a, temporary variable a to 1. So then in the next line, it's going to use that a, and it's going to produce a future of 1 plus 5, that's 6. It's going to extract that value, set the x to 6, and then eventually it will call yield, which is sort of equivalent to map in our chain of flat maps, and it will use that value to produce the string. So now we've got that fragment rewritten again using for comprehension. So first line is fetch user, extract user to user variable, and fetch Facebook friends, extract it to Facebook friends variable, and then we can use those variables inside of the continuation, which is in the yield expression. Now I'm going to rewrite the whole program to actually be entirely asynchronous and using for comprehension. So what I did is I took all these methods which were synchronous and then wrapped them with futures and wrote it using for comprehension. Now one thing to explain here is the underscores. So save, user, notify, and both notifies, they don't produce any values. They are just side effecting. So this is a way of telling for comprehension that we ignore the value of the container on the right. So that's why there are underscores there. Now it might not be entirely obvious that these two sections, the top and bottom sections, are not parallel. If you think about it, they translate it to chain of flat maps. And the way the flat map works is it only creates a new future, the inner future, if the previous future finished. So, so this is not parallel. This is synchronous but not parallel. But luckily there is a way. So I highlighted these two sections because expression in each section are totally independent. So fetching user, fetching Facebook friends, Facebook and Twitter friends is totally independent. So we can run it in parallel. There is a combinator in Scala futures. It's called zip. So if you have two futures, two started futures, and just call zip on one and pass the other, it will produce a future which will return a tuple of results. And it will only return when both of them complete. So using that zip combinator, we can produce a combinator which does it for arbitrary number of futures. So that's what I did. And I just called zip and passed all these three futures. They start immediately, and they will finish. The whole future containing a tuple of 3 items will finish when the last of these futures finishes. Okay, so let's take a look at durations now. So the first section will take 2 seconds because each of the longest calls takes 2 seconds. So the longest future takes 2 seconds, and they run in parallel. Obviously, that's assuming that we've got enough compute power to do that. The bottom section will take 1 second because the notifications each take 1 second, so they can be run in parallel. Now, so that the whole thing now takes 3 seconds. So that's great. We just managed to cut in half the duration of the whole request. But what is even nicer is that we actually, when you look at this program, it's not far from the original program. It's sort of the same program, but just without vowels. And maybe a zip makes it slightly different. But it's still the same readable program. And when you get used to that notation, it just feels good. So now the question remains, what have we done? Has it any influence on the throughput of our system? Remember that it was 166 requests per second. What do you think? Has it improved the throughput? Is it going to go down? Is it going to go up? Any ideas?
Go up, not enough.
Up or down?
Up, but not enough for you, for your problem.
Okay, let's have a look. So let's imagine we had 500 requests, which would hit our server at the same time. what we would need to do is we would, because we're running things in parallel, we would need 500 threads to go to Twitter, 500 threads to go to Facebook, and I'm ignoring fetching the user from the database because it's relatively fast, so we would need 1 or 2 threads to just fetch all these 500 user accounts in the meantime. So we already use 1,000 threads just to go to, to Twitter and Facebook. Then we would merge it. Just that would be really brief, like fraction of a millisecond. Again, we would need 500 threads for this, and then eventually we would have to send notifications. So 500 threads to send removed users, 500 added users notifications. Again, I'm ignoring save user because we would need then maybe 3-4 threads this time. So we've used all 1,000 threads, but what we've got 500 requests in 3 seconds, which means that we can do 1,000 requests in 6 seconds. So actually throughput stays the same. Why is so? Well, the problem here is that our threads, whenever they call external API, they are blocking. And this is bad. And let's see how bad it is. So in human terms, this is what the thread does actually. In human terms, serialization of requests takes 3 hours. Then the thread waits for 55 years, and then the response comes back, and it takes 3 hours to deserialize it. So obviously, in this 55 years, you can do a lot. So now, if we instead use asynchronous API, so after serializing the request, we would just say schedule or request that the write, asynchronous write, our thread could handle 100,000 similar requests in the meantime before the response came back. So that is so significant. So let's have a look at our function. Let's assume that we are using asynchronous I/O. So first 3 requests, they would take roughly 3 multiplied by 6 hours. So we're still in human terms, talking in human terms. So that's 18 hours. The bottom section will be around 13 days. The way I've calculated is I assume that there will be like 25 new friends and 25 removed friends. Obviously, it's maybe not very realistic scenario, but let's stick to this. So that in total gives us 14 days. And if you think about it, before it was 170 years. Now we've got 14 days of actual CPU usage, of actual thread time. Everything else was just waiting. So now, if we convert it back to normal times, that will be around 1.2 milliseconds. That means that we can do 830 requests per second on one core. Obviously, I'm fairly optimistic here because that we would assume that we are using 100% of the CPU all the time. But we're talking about the maximum throughput here. And if we had 2 cores, that would be 1660, which is exactly 10 times. And I must say, I didn't make it to look like that. That was accidentally, it happened actually. All these calculations I did is on the back of an envelope, so you need to take it with a pinch of salt. But the order of magnitudes are correct here. So now we improved our throughput 10 times by combining asynchronous programming and reactive programming with asynchronous I/O. Okay, let's talk about actors. So, what are actors? Actors are just objects, just regular objects, but with one difference. The only way they can communicate with the external world is through asynchronous messages. So this is the example of an actor system. I think Torben might like it because it comes from the telecom domain. So let's say we've got a phone connection actor. This is happening inside of your phone. Phone connection actor. That phone connection actor gets messages from microphone actor, and then does a little bit of noise cancelling and all that stuff, reducing feedback, and it would send it to the radio. Radio would send it to the person you talk to, then they would speak back, and radio would send some messages back to the connection actor. Then connection actor would do a little bit of smart stuff, and then it would send it messages to speaker. There would also be a keyboard actor, which would react to whatever you do with the keyboard and would send it to connection actor. Now, actors are not threads. So what does it mean? Well, actors are just objects which have a queue of pending messages. I like to think about actors as more like puppets in a puppet show. You need an animator to animate an actor. And this role of an animator is played by dispatcher threads. So dispatcher has a pool of threads. And what these threads do is they look for actors which have pending messages. And once they find such actor, they take a message off the queue of the actor, and then they animate the actor by calling its receive method. Now, when the message is processed by the actor, this thread goes and finds another actor, takes a message off the queue, and animates it. Well, that's in theory. In practice, what happens is, to avoid context switching, probably one thread would process more than one message for a particular actor. But there is no link between a thread and an actor, because what can happen is that the same actor can be animated by multiple threads, and the same thread can animate multiple actors. So I think that's a useful metaphor. Actors are puppets. Without threads, they're just dead. How would the actor look like? Actor in Akka just needs to implement the actor thread, and it needs to provide a receive method, which returns a partial function. And this partial function defines how actor reacts to messages. So our simple actor, what it does is it extracts A and B from the message, adds them, and then sends the response back. Actually, I didn't tell you the whole through when I said how dispatcher, I explained how dispatcher handles the messages. Actually, dispatcher, before it calls receive method, it sets a couple of fields on an actor object, and one of them is sender. So then actor can send a message back to the sender, and the exclamation mark is just a method call. It's just the name of a method. Instead, you can use tell, and that means send a message to an actor. And this is obviously non-blocking asynchronous call. This is just enqueuing the message in the queue of the sender actor. So now, how to create an actor? Actors live in actor systems, so you need to create actor system first, and then you just call an actor of method of a system, and in this scenario, we just give it a name of the actor we want to, name of the class of the actor we want to instantiate. So once we've got the actor reference, we can send a message to it. And in this example, actually, the simple actor will have nobody to respond to, because we are running this in the main thread, not within the actor context. So if simple actor responds to our add message, that message will get lost. It will be sent to the dead letter queue. But there is actually a way of getting responses from actors. So there is this thing called ask pattern. And ask pattern adds extra methods to actor ref, and in particular the question mark method. And what question mark method does, it creates a temporary actor. Actors are very cheap to create, by the way, super cheap. You can have millions of them. So it would create a temporary actor. It would send a message to our simple actor, and then it would return us a future. And that future will only complete when the simple actor responds to our message. So once we've got the response future, we can do the usual stuff with it. We can do on complete handler, we can pass it on, map, flat map, whatever we want to do. Now I promised that I will show you a practical example of actors. And I've chosen an example which is very close to me. It's wrapping the synchronous resource with asynchronous API. It's often the case that when you start writing the asynchronous systems, you will hit this roadblock that your drivers or your database drivers or HTTP API will be synchronous. So I'm going to show you like a universal way how you can deal with resources which are synchronous. So on the left-hand side, we've got a client. On the right hand side, we've got resource. I picked the database, and there is a connection. So you probably need more than one connection. What we're going to do is we're going to wrap those connections with actors. So each connection will have one actor. So one actor will wrap one connection. Then we're going to add a facade actor because we don't want our client to know about all the details behind the scenes. We just want it to talk to the facade actor. And facade actor will talk to the router. Router will know how to route the messages, and it will use. Oops. Oh, this is what happens when you use too much animations. So we've got router. A router will use load balancer to load balance the messages between actors, and it will use supervisor to deal with error situations. I think Torben mentioned some sort of supervision stuff. The Erlang and Akka have very similar stuff. Actually, Akka is really based on Erlang. Okay, and the last actor we don't have here is the monitor actor. So our connection actors will talk to the monitor actor and tell it about its status. So if the connection goes down or it goes up, monitor actor wants to know about it, and it will aggregate the state of the resource and will send it back to the facade actor so that facade actor can react accordingly. Okay, let's have a look what happens when the client sends a message. So obviously it sends it to the facade actor. Facade actor forwards it to the router. Router uses load balancer to send it to one of the connection actors, and that gets obviously executed against the resource. Now, if everything is fine, the result message is going to be sent directly to the client, bypassing all the other stuff. But what is more interesting is what's going to happen when there is a failure. So, when there is a failure, the first thing which actor would do is it would send the message back to the client to tell it something went wrong. Then it will send a message to the monitor actor to tell it, oh, my connection is in danger, is down. And then that error message will get propagated to the supervisor. And what supervisor will do, it will kill the actor. Yeah, so we want to fail fast. We want to clear the potentially corrupt state of a connection because we have no way to tell what caused the error, whether the connection is still in a consistent state. So it's easier just to kill the actor. And next thing happens is the supervisor spins the new actor and replaces the old actor with the new, and it sends the OK message to the new actor. Sends a message to the monitor actor to tell it, oh, okay, I've got one more connection working. So let's quickly look at what is sent over the wire. So that message is actually a function. It's a function from resource to result. So resource can be a database connection, JDBC connection, it can be JMS session, or some sort of object representing the connection to the resource. And the result is anything you want to return. I just created a command type as an alias. And now if we wanted to call our facade object, facade actor, I called our facade actor database in this case, we could just do something like that. We could just use ask pattern and just send some sort of command to it. Let's have a look at the connection actor. So first thing connection actor does is it opens a connection to the resource, and then when it's successful, it immediately sends a message to the monitor, the connection is up. Now, when you look at the receive method of our connection actor, it only responds to the messages which are tuples of the command and deadline. We are using deadline here because sometimes we've got a situation where there is a lot of messages which pile up while the connection is slow or down or something like that. And it might happen that there are some messages in our queue which nobody waits for anymore. So there is no point calling the database if nobody waits for the response anyway. So we throw these messages immediately away. So actually, if our command is not timed out, what we're going to do is because it's just a function which takes a resource and produces something, we're just going to call it, and then we're going to pass our resource to it, and then we send the response back to the sender. And as I mentioned previously, if something goes wrong, this pre-restart method gets called. And first thing we do is we send error message to the sender. We send a monitor connection is down message, and then we close the resource. Let's have a look at the Facade actor. So Facade actor, first what it does, it creates a monitor actor, and then what is more interesting, it creates a router. And the way to create a router in Scala and in Akka, it's very, very simple. What you do is you just say, okay, I want this connection actor to be wrapped by the router. And here is the load balancing policy. We're going to use smallest mailbox router. And by the way, this load balancing policy will use X number of actors, will spawn X number of actors. In our case, it's parameterized by connections variable. So let's say we want to have 5 connections. And then the next thing we do is we just say, okay, with supervisor strategy, and in this example, it's very simple supervisor strategy, no matter what exception is going to happen inside of the actor, just restart it. Just a question, how much time left do I have? Okay. Okay, and so there is one more thing which is very interesting here, is the dispatcher. I actually also, in this configuration, I say with dispatcher and then pass the dispatcher name. I said that there is, every actor system has a dispatcher, and dispatcher has a pool of threads. But in fact, we can have more than one dispatcher within actor system, and that's useful for situations exactly like this one. Because imagine that we had 5 threads in our pool, and we had 5 connections to the database. Now, if all these connections were blocking and waiting for the database to respond to us, that actor system will be frozen. Nothing else in this actor system could happen because all the threads will be used for dealing with database connections. So that's why we can create a separate dispatcher, dedicate a number of threads for this dispatcher, and have 2 dispatchers, 2 thread pools, and that way all the actors, all other actors in our actor system can still work fine. Okay, let's have a look at the receive method of Facade actor. Actually, I said that you can define the behavior of the actor by defining the receive method. But in fact, what we can do is during the while the actor is alive, we can swap that behavior. And what it gives us is our actor can have like an internal state machine. So what I do is I start the Facade actor in a state, I called it resources up. So when you look at the resources up, it's just a partial function. And what it does is when we get the command, it will just forward that command to the router. But when it gets the resources down message from the monitor, what it's going to do is going to use the context of the actor to swap that behavior of the actor. So it's going to swap it to resources down. So now we are in resources down state, and when any command hits us, what we're going to do is we immediately respond, this resource is temporarily unavailable. So we fail fast. So that's really nice. And obviously when we get the resource up message again from the monitor, when one of the connections starts successfully, we flip back to the resource up state. And last but not least is the monitor actor. The monitor actor starts in inactive state, and when the connection actors start coming up, they will send connection up message to the monitor actor. So that will flip it from inactive to active 1, then active 2, active 3. So number represents how many connections there is. Obviously, when we get a connection down message, it will reduce it from active k plus 1 to active k. So eventually, when we are in active 1 and we get the message connection is down, we go back to inactive state. And what's interesting about the inactive state, when we enter the inactive state, we immediately schedule a message to itself. The message, I called it inactive for a long time. And when that message, after a delay, let's say 5 seconds, hits the monitor actor, and it's still in inactive state, that moves it to inactive for a long time. And when monitor actor enters this state, it immediately sends a message to the facade actor, resources down. Because it was down for too long, we waited for a moment for the connections to come up, but now there is a little crisis here. So I better tell the facade actor so it can react accordingly. And obviously when we get connection up from connection actor, we go back to active 1 state and we send a message, resources out. Okay, I hope you enjoyed the part about futures and how to make your system more parallel without losing the simplicity. I hope that you're going to use more asynchronous I/O when you hit throughput problems in your systems. And I hope that example of actors will encourage you to experiment with actors in your systems. This is all I had today. Thank you very much. And now is the time for questions. So the question is, what's going to happen when a dispatcher thread calls a receive method of an actor blocks inside of that. It blocks the thread. That's the answer. So there is no magic bullet here. This is what's going to happen. It's not going to block the thread.
So this whole system isn't very asynchronous. It's still blocking, but we just kind of test the blocking part somewhere where we don't see it, right? So where's the game?
The game is that it's separated. So if you have dedicated the pool of this of threads for it, the blocking only happens in that pool. And if you want to win game, you want to use asynchronous IR.
Can we use block? There is a code block and with keyword blocks or blocking that we can put logging code in it. It will inform dispatcher that it should spell another thread because that part of code is blocking and it assumes it will work. And I think it will.
That's right. There is in standard library, there is a function called blocking. So if you wrap your expression with this, you're telling the dispatcher that there's something blocking going to happen, and that way dispatcher can spawn more threads. Depends on what sort of dispatcher you're using, but there is like a fork giant dispatcher which actually plays nicely with blocking keyword.
I don't know if you use this actor system. I mean, the between asynchronous and synchronous calls. Many Java libraries have user thread locals. Do you make a problem with that? So that you have to pin actor to thread so the Java library works correctly? Because library writers don't write. I use a thread locals.
There is a solution for situations like that. Actually, what I would suggest in this particular example, you can use the dispatcher, which has it's a pinned dispatcher, which means that you actually dedicate thread per actor. This is against the actor model, but in certain scenarios, like this one, where you have thread local stuff, or for I/O, where it actually doesn't pay off to do the context switching, it makes sense to have one thread per connection anyway. You can use so-called pinned dispatcher.
Well, I have a question. So the first three operations in your example were dependent, so you cannot do a lot about it. But what if you would not do all this magic, but only move the last three operations into like a separate actors and just fire them and go back to the user immediately? Would it this simple option just cut like 80% of the request time?
let's have a look. So you're saying that the first three operations are dependent. I would say they aren't. Fetch user, fetch Facebook friends, and fetch Twitter friends, they aren't dependent. The only reason...
sorry, so you cannot return after, faster than after the merge, yeah? So that was my idea.
Okay, you're right. I could return just after the merge, because I've got all the information to return. That's right. But there will be still a job to do. So I could return from HTTP request. That makes sense. Absolutely. That would make the HTTP request faster. Yeah. Obviously, this is just an example, right? But in your systems, you probably have situations when you can't, when you will have to wait until the whole thing finishes. Do you have any other questions? Okay, thank you then.